Hi students, so now let's go over another exercise. Well, I'm giving you also A, B and C, and we will like to see how the observer poles affect the state observer performance. So how selecting the observer pole will affect the state observer performance. So here we are taking two poles, two different dynamics for your observer. One at -10 as before in previous exercise, and one at -1. Well, first of all, you need to find IG of A. IG of A to know the stability of the states. So you have two states here, 2 by 2 matrix, okay? So second order system. So what? 0 minus 5, 1 minus 4. So then A is 0 minus 5, 1 minus 4. So that's your A. IG of it is -2 plus I, -2 minus I. So -2 plus I and -2 minus I. So those are x1 is stable, x2 is stable. So here the system is stable. In previous exercise the system was unstable, and then you saw when we represented visually, we saw it goes high. But here the system is stable. And the observer dynamic doesn't change the dynamic of the system at the end. It just, you are looking for a faster response than the existing x, so in a way x tend to x quickly. So then you know your observation is as if you have a sensors and measuring with any error, without error. So it doesn't change the dynamic of the system. We are not expecting to change the dynamic of the system. We are not designing K. We are designing KE or L, Lemberger, observer. It's not changing the dynamic of the system. Okay. So then now, okay, this is my closed loop pole. If I want to represent it on the S-plane, maybe here -2 plus. Okay. So the system is stable at -2. And here at -10, you have the poles of the observer. You have another observer at -1. So maybe -1 and another pole at -1. So I have two observer dynamics. Then I need to compare them and see how the observer poles affect the state observer performance, how it affects the performance of x tilde, how the location of your observer poles will affect the observer performance. We can clearly see from the S-plane that if it is here, it is faster, like here is 5 times faster, so then x tilde will tend quickly to x. That's what you should expect to see. However, in here you are even slower, so then it will take more time for x tilde to tend to x, because you make it slower than the performance of the open loop dynamics. So then it's not desirable to have a state observer in here. So look to your open loop and have it quicker than. And that's the idea behind this exercise. Otherwise, it's calculating it is easy. L1 and L2 acre or place A transpose C transpose -10 transpose, and L2 is the same acre A transpose C transpose -1 transpose. Okay, so here full state observer. I am observing all the states. That's why here it's ordered. Also, I have 2 poles as the number of states. So let's see it in MATLAB now. I go to my M5. Here we go. That's my system, and that's the 2 observer, and these are the to Lemberger vector. I need to check the observability always before anything. Check the observability first. And here you go with L1 and L2. Alright? And let's do a visualization in MATLAB to check everything. So now I go here. Well, if you wish. So now the same system, I have L1, and later on I go and replace L1 by L2. Alright? So let's now keep it L1, and so you see the system is stable, not going for infinity, because alright. So here vector x, and here is x tilde. Here is x and here x tilde. So this is output of the observer. Alright, so here is x tilde, and here is x. So x1 and x2, well, they are in different. Maybe best way is to have them on the same curve. Okay, so if that's what you like, you can easily do it. It's not that hard. What I will do is the following. Control Z, Control. Okay, what I will do, I will take this from here, copy it to here, alright, put it here. Okay, so we'll be visualizing two things, x1 and x1 tilde on the same. So this is x1, this is x1 tilde, and here x2, so this is x2 and x2 tilde, x2 tilde. So here I'll call it x2, yeah, I'll call it state 2, just, and here is state 1. Just a visualization purpose, nothing more. And here you go. We have x1 and x1 tilde, x2 and x2 tilde. Well, it seems for you, no, it looks like different. They are not, actually they are the same, but here we have initial condition for x1 and initial condition for x2. Remember, I am taking an initial condition of 1. So your observer doesn't know the initial condition. So then is working without initial condition, but essentially he should follow it in a directly. Then if you look at, is able to following it in a short amount of time. Even better to visualize it on, not like this, maybe better to have a mixer So here is a mixer. This is the mixer. Here is the mixer. Good. Yes, image. I will and here having it with only one port. Good. Same here. Having a mixer. Alright, so x1 was x1 tilde and x2 was x2 tilde. So here maybe easy to visualize. Okay, make sure that your layout in case. You see here maybe a better you can look at. So only the state x1 and x2, maybe you can view the legend x1 and x1 tilde, and here is the legend, so you know which one is x1. So x1 it has initial condition, and here x2 it has initial condition, but after it, and the observer start always from 0. So your observer starting from 0, but after some time it tends to it and following it perfectly. Okay, so that's your observer. So now we are quite confident that, well, even if you cannot measure state 1 and x1 and x2, you will be able to observe them. Okay, let me now just screencast it to my whiteboard. Okay. This is for L1, of course, and yeah, so here I have space for that exercise. My space for that exercise is here. Alright, and let's look to the other case of L2. So this is for L1 in green or in red color. Okay, L1, and here is for L2. So this design is for L1. Let's see for L2. Now in your Simulink, I simply will change L1 by L2. Alright, and I simulate the system, I run it, and let's see what state. Well, clearly the difference is seen. They follow it. It doesn't follow it exactly. You have a lot of error between them. See, a lot of error. So let's, for comparison, if you wish, let's take it there to the whiteboard and put them together. But I think it's clearly seen. Doesn't need really. Alright, so that's it for this exercise. Here it is for L2, and able to see the difference for both. Maybe if you wish to have them like this, so if you see better, you can look at both systems. I didn't. This is not the correct one. Here is the correct one. So the difference is very clear, right? Between both. So then it's not recommended to have a dynamic of the observer slower than the dynamic of the state itself. Better to have always faster than. Good. So let's go move forward now to the other exercise.